Image processing tools, and the reason I picked this is because I'm doing one of these hands-on things this afternoon, and some of this is relevant to what I'll be talking about this afternoon. So this is, it's kind of a random collection of things, but it's things that if you're closely familiar with all this stuff, then this will be very boring to you, I guess. But if you're not already extremely familiar with it, these are very useful tools to know about, and they're applicable to a wide range of problems, data analysis problems of all kinds. So it's very helpful to be aware of how it works. So to begin with, Fourier transforms. Probably everybody is pretty familiar with Fourier transforms. The key fact, and I'm focusing on discrete Fourier transforms. I mean, when you learn about them as an undergraduate or a graduate student, mostly people talk about the continuous Fourier transform, which is useful as an analytical tool for differential equations and things like that. The one that's powerful for computing is the discrete Fourier transform, and the reason is there's a super fast algorithm for it, which takes order n log n time to do a transform of n points. And the very important feature of Fourier transforms, which you probably all know about, is the convolution theorem, which says the Fourier transform of the convolution of two functions is the product of the Fourier transform of those two functions. So that is an algorithm then for taking a convolution operation, which can be a very time-consuming operation, and turning it into a much faster operation. Fourier transforms also occur naturally in radio interferometry. In radio imaging, what you measure is not measurements of the brightness of pixels on the sky like you do in almost every other mode of imaging. What you measure is samples of the Fourier transform of the image. So the actual data that you're collecting is in the Fourier domain. The data that you measure in radio interferometry is complex data. You measure for each data point, you get an amplitude and a phase for that measurement. And I'll probably talk tomorrow about radio astronomy, although again, I haven't decided exactly what to talk about for my third talk. But basically, when you have a radio interferometer, you have this array of telescopes. For every pair of telescopes, you get a measurement of a Fourier component of the image that's determined by the direction and length of that separation between those telescopes. Now, an important thing to know about this is that radio astronomers have for a long time been dealing with all sorts of kind of complicated problems in using Fourier transforms. For example, the fast Fourier transform is an algorithm for doing a transform of equally spaced data, where you have, for instance, a time series of data and all the points are perfectly equally spaced. It does not apply to unevenly spaced data or data with missing points and things like that. And a lot of times, when you look at real-world problems, you actually have data which is not perfectly evenly spaced. Radio astronomers have figured out, and I figured this out a long time ago, a way to get at least a very accurate approximation to the discrete Fourier transform using a fast Fourier transform. So you start out with unequally spaced data, you sort of convolve it with excuse me. You convolve it with a kernel function, you sample it onto an evenly spaced grid, you do a fast Fourier transform on that grid, and then you remove the convolution function effect. And what you get is the effect of doing the discrete Fourier transform, but in fast Fourier transform time. So if you have problems where you think, well, if only I could do this as a fast Fourier transform, it would be so much faster. We'll look to radio astronomy for clever ways to solve those problems, because they've done a lot of those solutions. Fourier transforms are complex valued. So you have, for each point, you start out with, say, an image, and what you get back is an image, but it's a complex image that has amplitude and phase. And it's useful to have a little bit of intuition about how these things work. One of the things that's kind of interesting and maybe surprising is that if you look at the amplitude and phase of a transform, the phase is actually the more important piece of information in a lot of senses. And here's an example. Here are two images. It's helpful to use images of faces because your eye and brain are very good at recognizing faces and details, okay? So if we take the Fourier transforms of these images, and we take the amplitude of the Fourier transform of Lincoln and the phase of the Fourier transform of Clinton, and put them together, and then take the inverse fast Fourier transform and look at what you get is that image at the lower right. And if you look at it, what you see is mainly Clinton. And the reason is the phase is the information that contains almost all the information about positions of objects in the image, about edges in the image, basically a lot of the things that your eye interprets as the structure in the image is carried in the phase. The amplitude just carries the information about the sort of overall location and shape of the image. So for instance, if you think about what happens when you convolve an image with a point spread function, if you have a symmetrical point spread function, it actually makes a real valued Fourier transform, or depending on how it's centered. And so all that does is when you multiply it in Fourier space, all it does is change the amplitude in Fourier space. It suppresses the high frequencies. So you can have images which look very much the same, but one is just a slightly blurry version of the other, which have very different amplitudes, but they have all the same phases. If you do the things the other way, if you use the phase of Lincoln and the amplitude of Clinton, again, what you clearly see is the phase of Lincoln. So this phase information is really important. In fact, there's a whole area of image processing called phase retrieval, where you have information where you make measurements of the Fourier amplitude of things, and you're trying to recover the phase information. It's actually possible to do that if you have sufficient constraints, and there's a lot of interesting applications of that. The other thing to know about Fourier transforms is the coefficients in Fourier transforms. Every one of those coefficients is measuring a global property of the image. And if you take a Fourier transform and you start fiddling with the coefficients, then what you do is you make global changes in the image. It's very hard to do something like take an image and say, okay, what I want to do is remove this feature in the image. In Fourier space, that involves changing every Fourier transform coefficient in the image, basically. Everything that you do requires global changes. And as an example, here's, again, one of these pictures. I changed a single Fourier coefficient. The Fourier coefficients represent sines and cosines across the image. So what you get is a sine, a particular frequency and direction across the image. So you can imagine that if you're trying to make changes by changing a small number of coefficients, here's a result of changing a block of coefficients, just 0.1%, just produces kind of a mess across the image. So what that means is while the Fourier transforms, understanding how it works and being able to use it is essential for the convolution theorem, the fact that everything is global and tied together, it's very awkward if you're trying to use Fourier transforms to do image analysis. They're often, unless the Fourier transform appears as the natural thing, for instance, as an interferometry, usually it doesn't make sense to try to use a Fourier transform to do image analysis. You need something which has a more direct connection to locality in the image. And that's where wavelet transforms come in. Wavelet transforms decompose an image into a sum of localized functions, unlike the Fourier functions, which are global across the image, which have various spatial scales. So a typical wavelet transform would have, you'd have a coefficient which represents something like, sort of the entire size of the image, and then another one which is sort of lumps half the size of the image, and there are 4 of those, and then another one 1/4 of the size of the image, and there'd be 16 of those, and so on. Because those functions are localized, you can make changes in the coefficients in wavelets, and they produce localized changes. So that makes it very powerful for image analysis. I'll describe a couple of transforms. The Har transform, which is the simplest wavelet transform, and in fact it was invented, this is a long time before people came up with the name wavelet in 1916, and here's the outline. So let me just walk through this. So you start out, I'm going to describe these in one dimension, but the application to two dimension or the extension to two dimensions is straightforward. I'll talk a little bit about that. So you have a vector of values, and what you do is you group these values in pairs, and for each pair you compute the sum of the pixel values, or really the average, and the difference of the pixel values. So you start out with 2 pixels going into each pair, and you get 2 values coming out, a sum and a difference. Okay, that's step 1. Then you repeat that, but you repeat it using only the summed part of the image. So you take all this version of the vector, you take the whole vector, which if you look at the sums has half as many pixels as the original one did. You do the same thing again. You group those sums in pairs, you calculate sums of those and differences of those. And you continue those reductions until only one value remains. So you've reduced the image down to a value which is essentially the average of all the pixels in the image. And that's all there is to it. There's really not a lot to it. The Har transform is the simplest, the lowest order example of a whole class of orthonormal transforms. They have various properties which are useful for certain things and not so useful for other things. One nice property is the transformed array is the same size as the original array, so you can do these transforms in place in memory, for instance. A negative property is it's not translation invariant. If you take an image and you do a wavelet transform of that image and then do some processing on it, for instance, to filter out noise, transform it back. If you take the image and shift it by a few pixels and then do exactly the same processing, what you get is a different result. You don't just get a shifted version of the filtered image. So that's the translation invariance property. It's not translation invariant. So you have to worry about that. That's an effect that can be important. A nice feature of the Har transform, and there's a whole class of these transforms which are implemented using something called the lifting scheme for computation. It can be made exactly reversible for integer calculations, which makes it really useful for data compression. Basically, you can do a transform of an image using this integer scheme. You can compress the result, which is more compressible than the original image, using any possible scheme. If you then invert it and then do the inverse transform, which looks very much like the Fourier transform calculation, what you get back is exactly the same value in integers. The extension to two dimensions is very easy. What you do is you do one of these reduction steps, bending the image down in pairs in the x direction, and then you do one reduction step in the y direction. So the effect is you take the image, which is a certain size, and you shrink it down by a factor of 2 in each direction. And then you iterate on that. So you take that image again, shrink it down by a factor of 2. Here's an example. So starting with the original image, after one step of the Har transform, here's the image bent down by a factor of 2. These are the y difference coefficients, and in fact you can look at it and sort of see that these coefficients are large in directions where you have horizontal things so that the y derivative is large. So effectively it's the derivative in the y direction, the derivative in the x direction, and this is a cross derivative. If you sort of trace through what happens to the pixels after you do these transforms in two different directions, this is essentially the sum of the two coefficients at two corners of a 2 by 2 pixel grid minus the sum of the pixels minus the sum of the pixels at the other two corners of the grid. So you repeat this, and the image shrinks by another factor of 2. Notice these other coefficients didn't change, so you don't, after you've done the first iteration, all the difference coefficients that you've already computed don't change. They're just locked in place. So if you look at the time to actually do this computation, most of the time goes into the initial pass through the image. That's the one where you touch all the pixels in the image. But then after the first reduction, you're only working on 1/4 of the pixel. So the time is 1/4 as long to do the calculation. And then when you get to the second one, you're only working on 1/16 of the pixels. So it very rapidly converges. So basically you touch every pixel 1 1/3 time. So the time to do this is basically linear in the number of pixels with a factor which is only a factor of 1.3 times the number of pixels in the image. So you repeat this and you have sort of Y difference coefficients, Y difference coefficients, Y difference. So there are all these sort of little shrinking images down to the bottom, and then there's one pixel down in the corner, which is the average of all the brightness in the whole image. When you do the inverse, what you do is you start out with these pixels down here, you add up the differences, and you reconstruct the tiny image in the corner and expand it by a factor of 2. Then you take the difference coefficients and you expand it by another factor of 2. So it's easy to figure out what the calculation is. It's a very simple inverse calculation. Here's another example of a wavelet transform. This is called the AstroInformatics transform, which means with holes because of the way the algorithm looks. There's a nice paper by Bijouy, Stark, and Murtaugh in 1994, which talks about this. This is an example of what's called an undecimated wavelet transform. So when you do this kind of transform, you don't get back an image which has the same number of pixels as the original image. Instead, you get back a stack of images, each one of which is the size of the original image. So it expands the amount of data that it takes to store the data. But it has the big advantage that it is translation invariant. So if you do processing using the AstroInformatics transform, if you shift the image around and do that processing, you'll get a shifted version of the result. So it's very helpful and sort of more robust for a lot of image processing. It's very simple and fast to compute. Here's the algorithm. So again, I'll describe it again in one dimension. You start with a vector of data, and then there's a kernel associated with the image. The kernel is of finite length. I give an example here of a kernel which has 3 elements. The typical kernel values that are used look like the polynomial coefficients divided by, or not polynomial, but binomial coefficients scaled so that the normalization is 1. So the binomial coefficients for 3 elements is 1, 2, 1. For 5 elements, it would be 1, 4, 6, 4, 1. So you take those as the coefficients. Those produce nice kernels. All right, so you take this kernel, which only has a few elements. You convolve the kernel with the data, and that produces a smooth version of the data. The smooth version of the data has the same number of pixels as the original image does. You subtract the smoothed version of the data from the original, and what you get is a difference image. Okay, that's step number 1. Now here comes the with holes part. You take the first kernel and you expand it by inserting zeros at every other position. So again, there are still only, in this case, 3 non-zero elements that you have to worry about, but the kernel extends twice as far as it did before. You convolve this new kernel with the smooth data to get a second level smooth data. And then you calculate another difference image by taking this second level smooth data and subtracting it from the first level smoothed image. So at every point, what you're doing is smoothing the image, subtracting it from the original image, setting that difference image aside, and then taking the smoothed image, smoothing it even more, subtracting it, setting that difference image aside. So you build up a stack of images, each one of which is a difference image, and they have structures at different scales in them. So the first one basically has all the sharp structures in it because you've taken an image which has been kind of lightly smoothed and subtracted it. So what you have left is only things which are relatively small and compact. If you have large structures in that image, the smooth version looks almost like the original version. So when you subtract it, there's very little left. But if you have very sharp structures, the smooth version looks very different from the original version. And when you subtract it, you have most of the sharp structure left. So you basically build up this array of difference images. And then at the end, you have one image, which is a heavily smoothed version of the original image. One of the easy things about this is that it's the inverse of this calculation is very simple. In fact, all you do to invert this transform is just add up the stack of images. You just add up the final smoothed image and all the difference images, you get back the original image. So it's a perfectly straightforward algorithm for inverting it. You repeat this for some number of levels. The number of levels that you use is somewhat arbitrary. It depends on your application. It depends on how large a scale you want. mean, one of the nice things about this is that the kernel doubles in size at each level. So basically the scale of the smooth over which the image has been smoothed is doubling at each level. But the amount of calculation that you have to do, because the kernel still is non-zero at only a few values, it's got lots of zeros in between, even though it's large, is the amount of computation it takes stays exactly the same, even though the kernel is getting broader and broader, because you're smoothing an image which got smoothed by a little three-element array, and then it got smoothed by this 5-element array with zeros, and then it becomes a what's next, 9-element array. So you add lots of zeros in there. So the kernel grows by a factor of 2 at each level, but the amount of work that's required to do the convolution does not grow. Again, the extension to 2D is very obvious. You do exactly the same calculation, except you smooth in the x direction and the y direction before you do the subtraction. So here's an example. This is a 4-level true transform. Here's the original image. So this is the level 1 image. This has the sharp structures. This is a symmetrical transform, unlike the Har transform where you had coefficients which had to do with x differences, y differences, and cross differences. Here, you're at every point, you're always looking at a symmetrical version of the smoothed image, and the difference coefficients are somehow not directional. So this basically has all the information about small scale structure in the image, and you can see it's basically an edge highlighting version. This is the next level, this is the next level, and here's the final smoothed image in this case. So very simple to implement this, but it has a lot of handy characteristics. And one of the nice things about the true transform is conceptually, because all you're doing is smoothing the image, taking a difference, and using that difference image, it's easy to fiddle with that algorithm for your particular application. If you have something that you want to do, for instance, one of the things that I want to do with the true transform, or with wavelet transforms in general, is do multi-resolution, multi-scale source detection. So what I want to do is be able to detect objects in images that are small and sharp, but I also want to be able to detect objects that are large and fuzzy. And that may actually be low signal to noise in any individual pixel. They may be kind of buried in the noise, but that are actually high signal to noise when you look at them in a low resolution version of the image. I have a version of the true transform that iterates the calculation of the smoothed image at each step, where if you smooth the image, you subtract it. If you think about what happens, if you have a star in the image, you smooth it and you subtract it, what you're left with is most of the star in the difference image, but then there's kind of a hole around the star because the smoothed version of the star is in the smoothed image. And so what you see is, when you look at these images, what you see is sharp things with holes around them. Well, once you know that there's a sharp structure in that image, which you can do by just doing the initial true smoothing difference step, you can exclude those pixels which were seen as having bright, sharp structures from the calculation of the smoothed image, so you can construct a better smoothed image which should not include holes around the bright stars, and is a better result for multi-resolution image processing. Sure. Yes. Yeah. Yeah, they're very, these transforms, by the time you do them in two directions, they're very close to circularly symmetric. They're very symmetrical. Here's an example. This is a Hubble telescope image of a galaxy cluster, Abell 1689. This is one of the strongest lensing clusters that's known. It has a very large Einstein radius. You can't see too much of it in this image, but there are a lot of arcs and things. There's a huge, tremendous amount of lensing here. It's a cluster at a redshift of about 0.17, I think. There are all these really large galaxies that are all overlapping in here, but there are also small objects. Doing source detection in this image is really complicated because what you want is to be able to identify the small objects, but then also to identify the large objects. There's a lot of overlap of objects. There may be faint things which are hard to see, but which are detectable as extended sources and so on. If you use source extractor, which is the most widely used astronomical source detection and cataloging program, this is, source extractor, I should say, has a bazillion parameters for tuning exactly how sources get detected. But we had a version of source extractor which we were using, the advanced camera science team was using to create catalogs from ACS images. And this is using the standard parameters that we were using for lots of ACS images. So they'd already been tuned to be good in general, although not tuned for this particular image. Anyway, these are the islands where sources got detected by source extractor. And in this case, it does a kind of a crummy job in a couple different ways. It doesn't do a good job of separating sources which are combined. And again, you could tune this to do better, but when you tune it, you lose other characteristics that are of consistency. Another thing is that the edges between the sources, you can see all the noise here. So there's a lot of noise in the definition of the edges of the islands. Okay, here is a version where I've taken the true transform. I've done this iterative version where I get rid of sources to produce cleaner versions of the difference images. And then I have a very simple algorithm for computing whether sources are detected. I look at the noise in the difference image. I do a simple thresholding of the image with, I can't remember what I used here, 5 sigma, I think, for detecting sources in the difference image that are above the noise. So you start with a sharp image, and it detects all these small things. Then you go to the second level difference image, which is smoother, is detecting smoother things. Again, you do the same thing. You calculate the noise, you locate islands in the image. And when you have islands in the second level image, there are several possibilities for them. They can show up in just independent places. They could be sources that you didn't detect. Those just become new sources. They could overlap an existing source. In that case, they're just extending the detection area, the segment that's associated with that source that you already detected. Or they can actually overlap more than one source, right? You can have more than one island, which includes, which it gets touched by an island that gets detected at a lower resolution. And the algorithm that I use to decide how to assign those pixels of this new, bigger island to, how to split them up among the older sources is a purely geometrical, morphological thing where I look at the moments of the distribution. So basically look at the ellipticity of an island that exists, and I look at the differences, the distances basically to all the potential islands that the pixel could get assigned to and how big those islands are, and do a simple geometrical assignment of this looks like, for instance, when you have highly elliptical things, it looks like these pixels over here ought to get assigned to that, but these pixels over here, which are off this axis, get assigned to this big thing. So it's a relatively straightforward algorithm, and it produces actually a much higher quality for this image, which is a hard image for segmentation, produces a much higher quality segmentation map for the image. It actually does a very nice job. So it's very helpful to be working in the wavelet space, in these sort of multi-resolution space, to do this kind of calculation. So this is what I said about how the algorithm works. It works in a relatively straightforward way. We talk about another application of wavelets, image compression. Orthonormal wavelet transforms, like the Har transform, keep the minimal information needed to describe the image. And I said that if you're doing integer calculations, it's possible to make them completely reversible. So they just keep the smallest amount of information that you need to describe the image. And in fact, they decorrelate the information in the original image in a very useful way, which makes them ideal for image compression. Either lossless image compression, where you get back the image exactly, or lossy image compression. In lossy compression, the goal, typically in astronomy at least, the goal is to discard the noise, or as much of the noise as you're comfortable with throwing away, while keeping the real structures in the image. So approximating an image using wavelet coefficients is a lot more accurate than other schemes. Here's another Hubble telescope image from the Hubble Legacy Archive. This is just the center of a galaxy ACS image. So this is an algorithm called H-compress, which uses the Har transform. So it uses this wavelet transform, plus uses a coding scheme for coding the coefficients. And it's a lossy compression algorithm. It discards information in the wavelet transform space. If you take this image, the original image was 32 bits per pixel. You compress it to 1.5 bits per pixel. That's what you get. 0.9 bits per pixel, 0.5 bits per pixel. And it's very hard to see the difference. So really, you can't, at this scale, see the difference. If I zoom in, then you can see what's going on. Here's the original image, 1.5 bits per pixel. There's a little bit of blockiness that's appeared there. I'm not sure if you can see that or not. 0.9 bits per pixel, the blockiness gets greater, but you can see the objects are still there, right? The objects are not disappearing at this point, although there are some faint targets, like there's an object right here, which is kind of disappearing. And then by the time you get to 0.5 bits per pixel, some things have definitely disappeared. So you can see when you zoom in enough, you can see that you've actually discarded real information there. The wavelet transform, though, does a very nice job on this. And for comparison, there are other algorithms for compressing images where you do, for instance, row by row. You take differences of rows of pixels in the image. And that's a reasonable way to do lossless compression of images. If you try to use that for lossy compression, where you don't preserve exactly the differences between pixels along those rows in the image, it does a terrible job. It produces an image that looks like this, where it's just full of stripes, because basically every tiny little bias that you introduce winds up propagating across the whole row of the image. So wavelet transforms allow you to make approximations in a space where you really can separate the noise from the signal in the best possible way. Finally, there are other ways that you can try to reduce the number of bits required to store an image. One thing you can do is you can just quantize the image. So you can, rather than keeping the image quantized at the original very finely spaced levels, you can separate those levels out and discard some quantization levels. If you try to compress the image to 1.65 bits per pixel, if you just quantize the image and then you do a lossless compression on this using an algorithm, what you find out is you can preserve very few levels of information. You have to grossly over-quantize it and throw a lot of information away. There are actually things you can do to make that better. This is an algorithm called subtractive dithering, where you have quantized levels with levels that are quantized the image with levels which are spaced actually at the same level as this image, but the actual positions of those levels is different for different pixels. So there's sort of a random map of exactly where you put those levels in the image. You can actually get much better results for image processing. This preserves a lot more information about the image than this does, but it still is much inferior to the wavelet transform version of the same image, which is actually using slightly smaller bits per pixels. So wavelet transforms are definitely the right thing to use in image compression. Now, something to think about is image and data compression. They have obvious applications. That is, you can store the images using less disk space. Well, we talked yesterday about how disk space is almost free. So why do you even need to bother with image compression anymore? You might wonder whether it even matters. Well, it matters because getting that data, moving that data around is what can take a long time. Reading the data off disk can be a very slow process for a large image. These compression algorithms are so fast that it actually can be considerably faster to compress the image, store it in a small compressed format, then read only that little bit of data, run your compression algorithm in memory, and uncompress the image in memory. So you can save time by reducing the I/O time and trading I/O for CPU. And CPU tends to be cheaper in this than trying to speed up your disk I/O rate. The same thing is true if you're looking at network transfers, where the bandwidth for moving data around is even smaller. And everybody's pretty familiar with the idea that it's, if you have a very big text file, it's much better to gzip it first before you transfer it, even though that takes some time, rather than transfer the huge file over. So another application where the data transfer rate is important is reducing the bandwidth between memory to memory transfers. And GPUs is a good example. And a lot of algorithms using GPUs, the real limit on the rate that you can do processing and the kinds of algorithms that you can use is set by the bandwidth to the memory of the GPU. So there's the way I think about it is the time it takes to do the processing for a lot of the algorithms that I use is totally dominated by the time to get the data into memory and get the data out of GPU memory. And the GPU itself is kind of free. Once it's in there, you can do a lot of calculations inside the GPU, and it sort of doesn't matter how much you're doing until the algorithm gets extremely complex. So this is another case where if you compress the data, send compressed data into the GPU and let the GPU do the uncompression, you may actually speed your algorithm up significantly. Here's another application. A classic use of wavelets is denoising. The way denoising images or data works is essentially one of the easiest algorithms to use is called wavelet coefficient shrinkage. What you do is you transfer the image into wavelet space. What you have is then all these difference coefficients. You take all those difference coefficients and you just shrink them towards zero. So you reduce the amplitudes of those coefficients. The positive ones remain positive but moves towards zero. The negative ones remain negative but move towards zero. Then you invert the transform, and what you get back is an image where the noise has been reduced, but the actual structures in the image remain. That's the same thing that really is happening in image compression. You're discarding information by reducing the amplitude of coefficients which are close to zero, basically bringing them down even closer to zero. Denoising is a helpful addition in deconvolution algorithms too. A brief note about deconvolution, which is something maybe some of you haven't thought about too much. So the idea of deconvolution is that images, all images, in fact, in the real world are blurred by a point spread function, which is set by the properties of the optical system that collects the image. If you have a spatially invariant point spread function, so if the point spread function is the same at the center of the image and at the edge of the image, then the mathematical effect of the point spread function is to convolve the image with a point spread function. If you want to undo that and recover what the image looked like before it got blurred by the point spread function, it's called deconvolution. It's an inverse problem. It's a problem that there's been a huge amount of work on over the years. There are algorithms, in fact, many of the algorithms that people use also can work on spatially varying point spread functions. So you can have a point spread function which is different at the middle of the image and at the corners of the image. They become computationally more challenging, but mathematically the algorithms look very similar. There's an algorithm that I could give you a talk about called the Richardson-Lucy algorithm, which what it is the maximum likelihood algorithm for doing restoration of data when the noise in the data is Poisson noise. So when the noise in the data is created by counting statistics. And actually this pops up a lot. Whenever you're doing analysis of data where you're counting things and you're asking about, well, what's the real distribution that underlies this? Because I have something which is kind of blurred or smeared my distribution. The Richardson-Lucy algorithm, once you're sort of aware of it, tends to just pop out of the woodwork as, oh, this turns out to be the right thing to use. So I've used it on things like, I have a program that I wrote that I use when I'm doing long slit spectroscopy of objects which are gravitationally lensed, quasars that have gravitational lensing. You have two objects that are very close together. You're trying to recover two images which are overlapping and figure out what is the inherent point spread function of those two images, which you don't know because it depends on the scene from the ground. There's an algorithm based on the Richardson-Lucy algorithm, which you can use to derive both the intensity of those two images and the shapes of the two point spread functions when they're overlapping. So it just pops up a lot. It's really a useful thing to know about. So here's a typical iterative deconvolution algorithm. There's a whole class of algorithms, and they all look essentially like this. You start with an initial guess for what the image looked like before it got blurred. That initial guess doesn't have to look anything like the image really does. In fact, typically the algorithms start out with an initial guess that says, oh, let's just assume there's nothing in the image. It's totally flat. You convolve your initial image with the point spread function to create a simulated image. This is, suppose my initial guess was correct, convolve it with the PSF. This is what I would have observed if my image were correct. You compute the difference between the simulated image and the observed image. So you find places where the simulated image is too bright or not bright enough. You use the differences to adjust the model image, and this is the step that depends entirely on which algorithm you're talking about. So there are lots of different algorithms. They differ, entirely in exactly this computation of the difference and the application of the difference to adjust the model image. But the idea is pretty straightforward. You have a place where the model image is too faint. Well, let's make our image that was before blurring, let's make it brighter there. If the model image is too bright, let's make it fainter there. So you basically adjust the image to try to get a better fit to the data, and then you repeat. So you take your new image, which has been adjusted. So all the details are in this step, and it's a straightforward idea. Well, so iterative deconvolution with denoising can work with any of these algorithms. It uses exactly the same approach, but it adds one more step here in the middle, which is you look at the differences between the simulated data and the observed data. The real data has noise in it. Noise is a big problem for deconvolution. So you have to be very careful about taking noise and over-interpreting the noise, trying to fit the noise too closely and producing a lot of spurious structures in your image. An easy thing to insert in here is denoising the differences between these using a wavelet filter. So you use one of these wavelet shrinkage approaches. You take that noise, you take that difference image, you sort of squeeze the noise out of it so you're left with only significant structures, and then you can proceed with your algorithm exactly as you did before. And that can have really miraculous results. So here's what happens with, this is a sort of, if you have, suppose you have a true image which is perfectly flat. You convolve it with a PSF, and what you get back is an observed image which is perfectly flat. But if you add noise, in this case I've added noise just as a little blip at one position, when you deconvolve it with the PSF, that noise gets amplified into highly oscillating structure, which is vastly bigger than the original noise was. And the reason is, if you take this structure with all these fast oscillations, you blur it with that PSF, it washes out. You have to make it brighter in the middle, so you put a big bright thing here in the middle, but then if you just put that in, then everything would get too big, so you have to put holes next to it so that the next pixels, so you wind up sort of overcompensating and then correcting for that and correcting. So every sort of tiny little blip in the image, if you're not careful about it, turns into something that looks like this in the deconvolved data. There are things that happen in deconvolution algorithms to avoid that. One of the things is, if this is down at 0, then you know that the image can't be negative. Images can only have regions, if you're looking at pictures of galaxies and stars, they only have positive brightnesses. There are no objects with negative brightnesses. So you could not produce an image that shoots below 0, the model image. And that can be a great constraint on your ability to restore the image, even without even worrying about noise at all. But this is a very important effect. It's one of two big effects in image deconvolution that you have to worry about. Here's an example of a deconvolved image. This is, don't know how many people remember this, but when the Hubble telescope got launched, it was discovered after the launch that the mirror had been shaped to the wrong prescription. It was basically too flat. The primary mirror of the Hubble telescope was too flat by, I think it was about 2 microns at the edge of the mirror. It's a 2.4 meter mirror. So it wasn't too flat by a lot, but 2 microns is a lot in optics. And the result was it had something called spherical aberration, which meant it couldn't be focused. There was no focus setting for the telescope, which could produce sharp images. The Hubble telescope produces great images now because we have a new suite of instruments which is installed starting in 1993 and then over the years, and all those new instruments include within them corrective optics which are designed just to correct for the fact that the primary mirror shape is wrong, and the result is the final imaging is just the same as you would have gotten if the primary mirror had been correct. But there were a few years there when it was touch and go whether the project was actually going to be canceled or not. Well, we did a lot of work at the time on deconvolution of images. This is what the images looked like. They're actually, the point spread function had a core, which was pretty sharp, but it only had 15% of the light in it. And then it had these wings with big tendrils, which were a big mess and extended over like 2 arc seconds or something like that. So the image had a very blurry component, plus a kind of a sharp component. This is Eta Carina. This is the original image from the wide field planetary camera, so uncorrected data. This is the Lucy algorithm version. This is basically run pretty much to convergence. And what you can see, all this speckling here is cases where the structure here had noise, and this is what the noise looks like in the image. If you see deconvolved images that look like this, where you see loads and loads of structure, you should know that what you're seeing is probably not real structure, it's probably just noise. This is what you get if you take the Lucy algorithm and you insert wavelet filtering in the middle. So if I go back and forth between these two, what you can see is that almost all the speckling is gone. It's actually done a great job, but it's preserved the sharp resolution here in the middle of the image, all the places where the signal to noise is adequate to recover the information. So it does a great job of controlling the noise amplification while allowing all the sharpening that the algorithm wants to do to happen. Now you might wonder whether this is actually a plausible result or not. You still don't know whether it's real or not. Well, fortunately, we do have high resolution images with the corrected telescope now. This is wide field planetary camera 2 image of Eta Carina, which was taken after the first servicing mission. So you can see that most of the structures we can see here are real. There are some differences. You might look at this and say, well, you know, it looks to me like this is still maybe too contrasty. It's too dark here in the middle. Well, we still have a point spread function in the data that we take from the Hubble telescope. It's a very good point spread function, but it's a point spread function. If we deconvolve that image, then what we get is an image which looks very, very similar to the deconvolved wavelet image. So this is evidence that deconvolution actually works pretty well. I mean, it certainly has its limits, but you can recover a lot of information. If you go back to the image that we had before that we started with, you've recovered a huge amount of information compared to that original image. And again, the ability of using wavelets to do this noise filtering is extremely valuable. So summary then, I'd say, you know, Fourier transforms, they're great to know about. You should definitely be using them if you're using convolutions. Think about with Fourier transforms, they're implicitly a periodic computation. So there are things that happen at the edges of images if you're doing Fourier transforms where there are wraparound effects with PSFs, for instance. But that can be taken care of. It's relatively easy to handle that. If you have cases where you have an image and there are bad pixels that you don't want to use, that can be taken care of. mean, there are a lot of things that you can do. They're relatively simple extensions of Fourier transforms. So if what you have is a calculation that looks pretty much like a convolution with some little tweaks, Fourier transforms is probably the right tool. And if you think about it, you can probably figure out a way to use it and speed up your calculation a lot. They're obviously key tools for interferometry where you're making measurements of the Fourier transform of the object, so you have to be using Fourier transforms to create an image. They're also key for period finding. If you're looking for periodic signals, well, Fourier transforms are the right things to be using. But you should use wavelet transforms for essentially everything else. Denoising, compression, multi-scale processing. They have a bazillion applications. They're certainly relevant to things like processing data in simulated images where you're trying to recover information from these complex calculations with billions of particles. Again, you know, multi-scale methods are definitely what you should be and what people are using there. And that's it. I write all my own software, so I like my own. Yeah, it's nice. I mean, most of these algorithms. I mean, I don't write my own Fourier transforms. I should say, you know, you can do that as an exercise, but there are great Fourier transform algorithms available. There are wavelet processing toolkits, but the algorithms, in fact, are simple enough that it's like 30 lines of C or 10 lines of Python or something like that to write your own. And in my opinion, it's very helpful to know what's going on down inside that algorithm and to be able to distinguishable difference between the measurements you make. One of the advantages of the wavelet algorithm, we've done tests, for instance, so you look at those images where basically the background is becoming blocky and you're clearly losing information on structures in the background. What happens if you take an image that's been compressed and you compress it as an individual image, but then you take 100 more images that are similar, and you compress all of those images, and then you're going to stack those up and try to produce a deep image. And you can show that as long as you keep about 1 bit in the noise and the accuracy, that the stacked image will have the same signal and the same signal to noise as you would have had by stacking the original image without any compression. So it has a much smaller effect than you might think on your ability to do science with the data in the compressed form. Mm-hmm. Shapelet, it is in the wavelet, I would say. Shapelets were originally created for, let's see, I'm trying to remember the whole story. They actually were created for gravitational lensing. I think that was the first application, although they were also doing applications to radio interferometry. But remember the whole, that they have characteristics. They're basically eigenvalues. They're like higher order functions, which are the next order things beyond Gaussian. I remember now how it works. Okay, so this is a this is a connection between.
Yeah. It's a connection between the wavelet and between wavelet domain and the Fourier domain. So a Gaussian is the function that when you do a Fourier transform of a Gaussian, you get back a Gaussian. So a Gaussian in the spatial domain turns into a Gaussian in the Fourier domain. Shapelets are the family of functions which all have those same characteristics. So they're higher order functions. A Gaussian is basically a blob. Then the next order is something that has like a positive lump and a negative lump in two directions, and say in the x direction, and then a positive and negative lump in the y direction. It gives a first derivative thing. There's a function which are the first order shapelets, and they have the characteristic that when you transform them, you do a Fourier transform of those functions, what you get back is a function which has the same shape in the Fourier domain. And they were interested in using this for radio imaging. In fact, they were interested, this was Alex Refrigier, is that his name? He was a graduate student at Columbia and was working some on the first survey. They were interested in doing weak gravitational lensing using the first survey, but when he looked at the images that came out of our pipeline processing using APES and all the radio imaging software, they have tremendous weird biases and characteristics. The image shapes were just not suitable. So he wanted to go back to the visibility data, back to the data which is measuring things in the Fourier domain, and figure out a way to process them so that he could pull out these sort of weak elliptical shapes for looking at weak lensing signals in the radio data. And that was why he created the shapelets to begin with. So there are a whole family of functions, but they have things in characteristic with wavelets, in that there are scales that they have where they're modeling things over different scales. But they have things that are different too, like they're not mostly wavelet basis functions. The ones that are easy to work with are the ones that are finite in size and are zero outside some size. Shapelets are not like that. They're like Gaussians. They sort of go on to infinity, even at a very low level. Shapelets also have some funny characteristics. There's sort of if you're trying to model the shape of an object using a sum of shapelets, you can do this shapelet expansion. So you're expanding the thing into a sum of a bunch of functions. There's an independent scale factor that you have to pick to say, okay, how big is this object and which scale shapelet should I be using? And they don't converge very well when you try to go to higher orders. They're sort of good at low orders, but when you get to higher orders, they don't extend very well. But they're definitely related to. There are also things you'll hear about, curvelets, which are sort of skinny directional wavelets, which are good for things like gravitational lensing, filtering, or detection. What's that? Chirplets. Chirplets are things that have frequency components which sort of shift across the object. So there are a lot of variations of these. And again, the algorithms tend to be pretty straightforward for all of them. Although I have to say I've never figured out how to implement curvelets myself. It's sufficiently. I think you have to be French in order to read the papers that the French mathematicians write in order to understand them. But anyway, there are many applications, and they all have in common the characteristic that you're creating coefficients which describe local structures, and which then you can manipulate to affect local changes in the